So in this discussion of method of variation of parameters, we are going to see another question. So you can listen to this. So you can see the question. It is given: solve the given differential equation d square y by dx square, d square y by dx square plus you have another term, that is 4y plus 4y is equal to x sine 2x. So you are told to solve this question using method of variation of parameters. The same kind of question already we have seen in second order differential solving as type 5. Here we can solve the same question using the concept of method of variation of parameters. Here the first step is the same. You will be finding the complementary function. So what is the procedure involved? First you have to find the general form of this. How will you write the general form of this? This could be written as d square y plus 4y is equal to x sine 2x. Then you can take the y term as common outside. So that you get d square plus 4 of y equal to x sine 2x. Now you can find the auxiliary equation. What is the auxiliary equation? You can take the bracket down. So m square plus 4 is equal to 0. From which you will find the roots. So m square is equal to minus 4. So m is equal to plus or minus root of minus 4. Still, you have a minus term inside the root, so you can split this. So root of minus 1, root of 4. So root of minus 1 is I, root of 4 is 2. So you have a complex root here. So this can be rewritten as m is equal to 0 plus or minus 2y. So what is the complementary function formula for this? What is the complementary function? Cf is equal to e power alpha x a cos or c1 whatever, c1 cos beta x plus c2 sin beta x. This you can substitute. The value of alpha is 0, beta is 2. So you get e power 0x c1 cos 2x plus c2 sin 2x. Now, what is the next step? What is e power 0? E power 0 is 1. So CF is, what is CF here? c1 cos 2x plus c2 sin 2x. So once after finding the complementary function, we can go for the particular integral. You know, particular integral formula is Pi is equal to u1 y1 plus u2 y2. This is the particular integral formula or general form for the method of variation of parameters. In order to find the particular integrals, here you have u1 y1, u2 y2. So from where we get y1 and y2? We get from the CF. That is, the coefficient of C1 is your y1, the coefficient of C2 is your y2. So your y1 is cos 2x, your y2 is sin 2x. Now we have to differentiate y1. What is the differentiation of cos x? Cos x differentiation is minus sin x. Differentiation of cos 2x. It is similar to cos ax formula, that is minus a sin ax. Minus a sin ax. So minus 2 sin 2x. Similarly, you will find y2 dash. So here this sin differentiation is cos. So sin ax is 2 cos 2x. So 2 cos 2x. Now you can proceed with the Wronskian formula, because in order to find u1, u2, we need to find w Wronskian constant. So that is w equal to y1 dash, y2 dash. So you substitute these values here. So that is y1 is cos 2x and y1 dash is minus 2 sin square 2x. Similarly, y2 is sin 2x. Then y2 dash is 2 cos 2x. Now you can cross multiply, since this is a kind of determinant idea here. So when you cross multiply, you get 2 cos square 2x. Then minus minus plus 2 sine square 2x. Now you can take 2 as common outside. So what you get? So 2 as common outside. So can you get cos square 2x plus sine square 2x. So it is of the same kind, cos square x plus sine square x idea. So what is the cos square x plus sine square x idea? It is equal to 1. So this is similar to cos square 2x plus sine square 2x. Okay. So you get here 2 into 1 which is equal to 2. Okay. This is how you will find the W. Okay. So after finding W, you can work for U1 and U2. You can work for U1 and U2. So as we discussed here, you have got W as 2 here. Now you can find U1 and U2. So U1 will give you, that is U1 formula will give you the answer, like if you use the formula minus integral y2 f of x by w dx and your y2, that is integral y1 f of x by w dx. These two results will give you the terms required for PA. Okay. So with these two ideas, we can connect with the terms given here so that you will get the particular integral. Okay.